In today's lesson 11.4, we're going to simplify rational expressions. Not rational numbers, although we'll look at them, but rational expressions, because you know how to do rational numbers. So a rational number is a number that can be written as the quotient of two integers. So types of fractions, 1/4, 27 over 32, 7 over 1. An example of a value that is not a rational number would be pi, because pi is approximately equal to 3.14159, and it keeps going. So we can't write it as a fraction. We can't, because it just keeps going on forever. And again, we are going to be looking at rational expressions, and a rational expression might look like the following. So here I have an example of three rational expressions. They're separated by semicolons. So 3 over x plus 4. So some of these are already simplified, and then some of them we can simplify a little bit. Actually, we can't simplify any of these. But these are all rational expressions. It would be undefined if the denominator were to be equal to 0. So when we're solving our rational expressions in a little bit, if we ended up getting something like an answer of -4, -4 can't be a solution, because -4 plus 4 equals 0. And we know that when we have 0 in the denominator, that's undefined. Oops, a little bit too quick. So to simplify a rational expression, we're going to divide out common factors from the numerator and the denominator, and we're going to look at a couple of examples, and we're going to start with numbers first. So you are quite familiar with something like this, where we have 28 over 35, and in our brain we'd probably just say, oh, divide by 7, divide by 7. But what I did here is I factored it just to show you the difference between numbers and expressions in a little bit. So because 7 times 4 is 28 and 7 times 5 is 35, we can cancel out the 7s once we turn it into multiplication, and we get an answer like 4/5. When we start looking at expressions that might have addition signs and subtraction signs, we have to factor it. You can't simplify if it has addition and subtraction, and I'll show you why. So let's just look at our 28 over 35 example. I know that 28 is the same as 5 plus 23, and 35 is the same as 5 plus 30. And if I cancel out my 5s, I get 23 over 30. That is not the same thing as 4/5. So when we look at our expressions, sometimes students think, oh, I can cancel out this x and maybe one of these x's, and that is illegal. You can't do that. We have to factor it. So if you remember, I always say, ask yourself, is there anything I can factor out? Another thing you ask yourself, do I have perfect squares at the front and perfect squares at the back? And what we have here is that we can factor out a 3x and a 9x squared. So now it's at a point where you can actually simplify. So take a moment and see if you can simplify it. Pause your screen. Okay, so we're going to check to see if you got it correct. So this says all multiplication. It's saying 3 times x times the quantity x plus 5. So because we have the quantity x plus 5 and x plus 5, you can cancel those out. You can reduce the 3 and the 9, just like if I had a plain old 3 over 9. And then we can reduce our denominator, our x squared, we can reduce it by 1x. So hopefully you got an answer of 1 over 3x. So we're going to factor this one. We had the difference between squares. We had a perfect square at the front, perfect square at the back. And then on the bottom we said in the denominator what multiplies to -2 and adds to 1x, -1x. So we went ahead and factored. Now we're going to try to simplify this. And it looks like we should be able to cancel something out, but it's not looking quite right. So pause your screen and see if you can figure this one out. All right, so the groups, the binomials that seem like we should be able to do something with them are these two. And you just have to be really careful with these minus signs. And if I manipulate it a little bit, I can get those two binomials to look the same. So what I'm going to do is factor out a negative. By taking out that negative, I end up with x minus 2. So if I said negative times x, I'd get negative x, which is right here. If I said negative times a -2, I would get this positive 2. So always make sure you're just not randomly taking out a sign, but that it actually is going to rework your problem enough so that you can actually create the same binomials. Now we can cancel out our x minus 2's. And it doesn't really matter where your minus sign goes or your negative sign, but typically you'll see it in front of the fraction bar and not necessarily in front of the numerator or denominator. Okay, I'm going to remind you again that if our denominator is equal to 0, it's undefined. So some of your homework examples might just ask you, when is the rational expression undefined? So all you need to do is factor the denominator, and once we factor out, find out what multiplies to -30 and adds to -7, then we're going to use our zero product property. X minus 10 equals 0, x plus 3 equals 0, and we come out with 10 or -3. So if it's equal to 10 or if it's equal to -3, then the rational expression would be undefined. One more slide. All right, remember to pause the slide at any time so that you can take down some notes. But basically this one says geometric probability, which we looked at in geometry. If we take region B and we put it over region A, which is what I did down here, then we're going to factor. I can factor out a 2x from my 2x squared plus 8x, and I got this ratio, and then from there we're just going to reduce. So jot down your answer and then I'll tell you what I got. Okay, so we canceled out our x plus 4's. We could take out this x and this x. So in the numerator we're left with nothing but 1, because when I say x plus 4, they go into each other one time. So I end up with 1 in the numerator, and in the denominator I ended up with 4x. And we'll do some practice problems in class.